Pleasure to be here. Thanks to Grant and Tally for the invitation today. I'll tell you a little bit about network energy in our industry. And right up front, this is not a green environmental talk. My colleagues at Bell Labs know that the joke is that I say I'm not interested in saving polar bears. They're pretty cute and so forth. But this is really about some technical as well as business and economic challenges that are tied to energy. And it's not an alarmist talk, but it points to certain trends as well as some opportunities and challenges that we have going forward. So I'll try and convince you that this is maybe an interesting area if you're an engineer. This is a good topic to work on. There's a lot of interesting problems and a lot of opportunities for all of us. So let me just give you a couple of numbers on where we are today when we talk about energy in the ICT industry. If you look at this chart, it shows that the total energy of all the devices in the ICT industry, so that's all your laptops, your phones, your smartphones, your tablets, consume about 39 gigawatts of power on an annual basis. And if you don't know what 39 gigawatts means, that's about 7 New York cities. So I leave it up to you to judge whether that's big or small, but that's sort of the scale that we're talking about. 7 New York cities, it's all the devices that we have. There's a good trend, though, here. If you look at the right side of the chart, most of the energy is in the personal computers. And as we transition more to tablets, smartphones, laptops, so forth, a lot of that energy is going from the devices that consume a lot of energy today to devices that are much more energy efficient. So the trend in the devices is sort of in our favor. Of course, we're all worried about battery and lifetime, daily use of our phones and smartphones. But generally, the trend in terms of the total energy consumption, it's going in our favor. Now let's look at the network side. On this chart, if you look at the network itself, we consume about 69 gigawatts of power on an annual basis, and that's about 12 New York cities. So the devices are about half of the network in terms of energy consumption. And here, the trend may not be so favorable. The different blobs on this chart from the left to the right show the home enterprise networks, the access network, wireless, fixed access, and then your core backbone networks, as well as then the data centers. And the size of the blobs is proportional to the energy. So you see a lot of the energy is consumed in data centers, which we know, but also a lot of the energy is just consumed in the wireless, primarily the wireless, but also the fixed access network, the home enterprise networks. And those are really your RAM bonds to the internet itself. By the way, I should mention that these charts, a little bit of an advertisement, these charts are taken from a tool called GWatt, which Bell Labs released publicly in early April, gwatt.net. If you're interested, it's freely available. Go check it out. It's a pretty cool app where you can play with different technology scenarios, different traffic growth scenarios. You can really see where the energy is consumed in the network, some hot zones in the network, and then as you change technologies, you can see what the impact would be in terms of energy consumption, cost, carbon, and so forth. And it's not because we developed it, but I think it's a pretty cool tool, and I hope you enjoy it if you go and play with it. So this is sort of the situation where we are today in the networks, the devices. But what's going to happen in the future? And the question really, somewhat provocatively, is can we afford the future of communications? All of us, we know we want to do more. We want to do more video. We want to maybe take all the SMU classes online. People in different parts of the world want to communicate. We want all of our apps available 24/7, all the devices everywhere. And we want to do more. We all want the high-definition video, the 3D video, the holographic images, everything. And of course, that will mean that we consume a lot more energy. We need bigger networks. We need more networks that handle this traffic. And the question is really, how much do they consume? Of course, the new technologies will be more energy efficient. But if you look at the traffic growth and you look at the network energy efficiency improvements, the two trends are not matching, in the sense that traffic is growing by factor 10, by factor 100, pick your favorite estimate, but it's between 10x and 100x traffic growth in the network, but the energy efficiency improvements are not keeping up with that traffic growth. So over time, you'll see that, yes, the energy efficiency is improving, but your net energy consumption is expected to grow. And that, of course, means that your energy bills will grow. Even today, the large operators in the world, without naming anybody, are typically the largest single consumers in their country from an energy perspective, spend about several hundred million euros, dollars on the electric bill. And generally, about 70 to 80% of the energy bill is going to the network. So we can expect that trend to grow. We can expect the cost of the energy to go up as well. So even if traffic doesn't grow, even if you don't change anything in the network, the cost per kilowatt hour is expected to double in the next 10 years. So that means that if nothing changes, you should expect your electric bill to double in the next 10 years just based on the cost of electricity going up. So if you say it the other way, if you want status quo, you need a factor 2 improvement in energy efficiency. So no change in traffic, no growth in traffic, just the cost of electricity. We need already factor 2 improvements in our efficiencies in our network. And that's sort of the view on the Western world, the developed countries. If you look at other parts of the world, you don't even have access to power. So even if you want to take your equipment and plug it into a power grid, you don't even have a power grid. Or you have a power grid for 2 hours of the day, which may not be the time when you really want to communicate. So a lot of the challenges in other parts of the world, maybe rural areas, developing countries, are really tied to the availability of the power, as well as where you want to deploy your communication. This is also starting to become more of an issue in our part of the world when we get to a densification of network, and think small cells. Think you want to deploy 20,000, 30,000, 50,000 small cells. Where do you want to deploy them? Really where the traffic is. But you always have access to power there. If you want to deploy small cells on lampposts, kiosks, side of buildings, you always have access to a power line there. Maybe not. So in that case, you spend a lot of energy to actually run a power line, a lot of money to spend a lot of money to get power to where your communication equipment is. So really, this is starting to become a constraint on where we deploy equipment and how we deploy it. If you look at the cost of deployment of small cells, the cost of providing a backhaul connection and the cost of providing a power connection are the 2 single most important elements in the total cost of deployment of small cells. So if you think about deploying 100,000 small cells, how is power and availability of power going to constrain that deployment? So my thesis is that if you look at the current trends, while we can still handle everything from an energy perspective today, the trends are not in our favor, and maybe that huge traffic growth that we all expect and we all want, because from a professional perspective, we want the traffic growth to happen. That just drives more equipment sale. From a personal perspective, we want the traffic also to happen because somehow we get value from all the applications, the services, and so forth. But the question is, can we really sustain it? And my thesis is, with the current trends, we can't. So now, what can you do about it? Now imagine a world where you could communicate with zero power. Imagine you could have all your applications, all your services, everywhere you want, but zero power. Okay, so now you should tell me that I haven't had my second cup of coffee. I'm maybe in labor stage as opposed to talent stage, and this is completely crazy and doesn't make any sense. So I'll tell you why this may not be as far-fetched as it sounds. So first of all, what do I mean by zero power? There are really 3 zeros. There are 3 dimensions on the zero power. The first one is zero grid power. So of course, if you could get completely off the grid, all the challenges that I mentioned about deployment, access to power, cost of deployment, availability of power go away. You just have locally, you harvest all the energy that you need to power your equipment. So that would certainly be desirable. Do you think that's achievable? Well, certainly from a technical perspective, there is no problem with doing that today. Technically, we know data centers use a lot of renewable energy already today. You have a lot of wireless base stations in deployment in developing countries that use solar panels. You can certainly take any of your small cells, buy a solar panel, dimension it correctly, and there you go. You're standalone. You have a big battery for your night operation when you have cloud cover and so forth. So certainly, technically, zero grid power is possible today. There's really no technical challenge. The challenge is it's not practical, it's not economically viable, because if you look at the size of the solar panel that you would need to power a small cell, it's going to be huge. And we talk about small cells as having a small coverage area, but also we want these small cells to be physically small. If you deploy 50,000 small cells on lampposts and side of buildings, you don't want them to be big. But if now you want to power them by renewables, the size of the small cell might be this, might be a shoebox, but the size of the solar panel that you need is several square meters. The size of the battery that you need would be several 100 kilograms of battery. So this is certainly not practical today, but it's definitely doable. So I think one of the research challenges really, can you get the efficiency of your renewable sources up, and can you get your energy consumption of the equipment down so that you match what you can harvest with what you need? And most of the challenges are really on the consumption side, because if you look at solar panels today, the theoretical efficiency of solar cells is in the 40%. So you have a factor 2 improvement there. Solar panels as a module are in the 30% efficiency, so maybe you can At best, you can do a factor 3. But we're really talking about getting the consumption of the equipment down by factor 10, factor 20, so that the size of the solar panel that you need blends into the equipment. So can you imagine a small cell, wireless base station, any equipment that you deploy where the solar panel would be completely invisible? It's really integrated into your equipment. Okay? I think it's doable. I think this is really doable. The second zero is zero wasted power. This one, I think we can get very close. I'm not as confident on this one as on the first one, but I think we can get very close. Zero wasted power means really all your overheads. If you look at any equipment today, whether it's wireless, any router, any switches, sometimes we spend half of the power just to cool the equipment. We have inefficient power supplies, we have inefficient cooling, and this is really power that's wasted. No offense to any of you who are working on thermal management or cooling, but cooling doesn't do useful work. Cooling is something that you need to do to run the equipment, run your packet processors, and even make sure they don't overheat and they don't break. But cooling itself doesn't do any useful work. So if we can get the wasted power down by making sure the overhead is zero, or as small as possible, we win. And it sounds any joule that you spend is really doing useful work for you. It's processing data, it's storing data, it's transporting data. Also, a lot of the equipment, if you look at it today, even if the equipment doesn't handle any traffic, you still consume a lot of power. Sometimes it's 70, 80, 90% of the peak power is consumed even when there's zero traffic through the equipment. So talk about wastage. Especially some equipment is not used that much. You think about wireless base stations in rural areas where you don't have a lot of traffic, you don't, excuse me, you're not always at peak power or at peak traffic, but you're spending a lot of energy just to keep the equipment up, even though you're not handling any traffic. So making sure that the power you have, the energy you spend is proportional to the actual traffic you send through the equipment, and making sure your overheads are small is definitely a goal to achieve. Now, it's never going to be completely zero, but I think it could be epsilon. And it's certainly a research goal to try and drive that wasted power down. The third one, on zero energy per bit, is probably the hardest one. And this is where it's a little bit crazy, because zero energy per bit is really not achievable. But what we're saying here is we want to get as close as possible to the fundamental limits of the energy that you need to transmit a bit. Okay, so it's zero unnecessary energy per bit in some sense. And again, today we spend a lot of energy and we're very far from the energy limits. So if you collect energy from your renewable source, you reduced all your wastage. So the one joule that you spend is the most efficient joule that you have. Now you want that joule to process as many bits as you can. Right? That's really energy per bit. If I do spend power, how do I get the most of the work done by that joule that I spent? And so I'll tell you a little bit about the Green Touch Consortium. How many of you have heard about Green Touch? All right. So I'll go a little bit longer introduction if you let me. So Green Touch was a pre-competitive research consortium that was founded in 2010 at the initiative of Bell Labs, but includes now about 50 members globally, industry, service providers, equipment providers, research institutes, universities, really across the board, with a goal to improve energy efficiency in networks by a factor 1,000. So if you look at the energy efficiency per bit today versus what's theoretically possible, there's a huge gap. So this is not talking about where the power comes from. This is just how much energy does it take to process and send information through the network. Whether the network is a wireless, a fixed access, a metro edge backbone network, just across the board. And we gave Green Touch a 5-year time frame with this ambitious mission. We said in the 5-year time frame from 2010 to 2015, we want to come up with a roadmap, a research roadmap of how you make networks 1,000 times more energy efficient. Now, it's very different from your typical research programs in two aspects. First of all, we gave it a 5-year time frame. Researchers are very reluctant to commit to a time frame at the beginning of the research when you have no idea how you get there. And the second one, we're not talking about a small improvement, we're talking about a major improvement of a factor 1,000, and we want to actually demonstrate how to do this, not just do paper studies, but actually do technology demonstrations on some key technologies on how to do it. So now, the question is, we're 2014, and I said 2015 is the target time frame. You should ask me how far we are on this journey. And this chart shows some result that we published about a year ago on progress that Green Touch has made towards that factor 1,000. And there are two things that come out of this study. The first one is when you look across the board from a fixed network, a wireless access network, as well as the core backbone networks, you have tremendous energy efficiency improvement opportunities. So the goal is, in some sense, achievable. But also, the improvement opportunities depend on which part of the network you talk about. If you go to the core network, you rely a lot on optical communication, which is inherently much more energy efficient already than wireless. In wireless, you basically radiate all around you. Air is a very inefficient medium for transmitting information compared to fiber. So your improvement opportunities, while they exist everywhere, are smaller as you get deeper into the network. And what we've shown last year is that in wireless, we can already improve energy efficiency by a factor 1,000. In fixed access, your copper, your optical access networks at home, we can improve energy efficiency by a factor 500. And in core networks, we can improve energy efficiency by a factor 100. So what this means, so those are the energy efficiency improvement factors in terms of energy per bit. But what this really means when you take these energy efficiency improvements and you couple it with traffic growth is you can have a net energy reduction in future networks. So if you imagine that you would build networks based on these technologies and you would deploy them, you can handle traffic growth while still have energy consumption go down on a net perspective. So the initial trend that we saw of traffic growing, energy having to grow with that traffic growth, we can actually decouple that. So the basic result of the study says that if you apply these technologies uniformly, and you look at the traffic growth between 2010 and 2020, and you apply these technologies on future 2020 type networks, the net energy consumption could go down by a factor 90% compared to 2010 while still handling that traffic growth. So obviously that would be pretty major accomplishments if you actually built networks on this. We're confident in the research we've done, but it's important to understand that this is just research. A lot of steps need to happen in terms of building technologies, standardization, deployment, so forth. You also need to look at some other aspects that are not considered in terms of rollout plans, backward compatibility, and so forth. So we believe that Green Touch has made quite a bit of progress on that 5-year journey. We have 1 more year to go. We believe we can improve on these numbers, especially on the wireless side. The fixed access and core network side, we're pretty confident in the final numbers. Wireless, we believe we can improve these numbers further. I don't have any numbers for you yet because that's still ongoing work. And then the other part that's really important is to understand which of the technologies contribute how much to that efficiency gain. Is there one technology that gives you the biggest jump in efficiency, or is it really a number of technologies that contribute equally? So understanding the overall impact on energy efficiency, as well as the relative contributions, is really key out of this work. And we have some specific key technology demonstrations that are planned for later this year and then going into next year. So you can expect to hear a lot more from Green Touch as we get sort of into our final event in May 2015 with updates on these numbers as well as specific technologies. So then when you're in research, you always look further. So the question is, you have this Green Touch result, what do you do after that? What do you do after May 2015 when Green Touch accomplishes its mission? And one of the things that we're starting to become much more interested in is the Internet of Things. And I think a lot of people talk about the Internet of Things. I want to expand the definition a little bit to include all your objects. Everything, all your stuff, everything that's in your world, everything you want to know about your objects, other people's objects. Who has a blue car that's the same model and brand as mine? You want to know something about the world. And if we get to this hyper-connected world, what is the impact from an energy perspective? A lot of people, in my opinion, have talked about the Internet of Things from an application perspective, from simplifying our lives, whether it's professional or personalized, but we haven't really looked at how you power this network. What is the impact of 100 billion devices on the network from an energy perspective? We worry about the device itself. We say this is a wireless sensor that we deploy and has to be connected. Sure. But what happens after the sensor is connected to the network? Especially if these sensors are wireless sensors, they almost have to be pretty dumb because they can't have a lot of functionality because they don't have power. They have to locally harvest their power because you're not going to run power lines to 100 billion devices. You're not going to run people around changing batteries on 100 billion devices. So if a lot of these devices are wirelessly connected, they will have to have very, very low functionality. So they'll do their measurement, they'll get their information from their local environment, and they send it out. So a lot of the handling of the information, a lot of the processing, the intelligence, the storage of the information has to be done in the network. So what's the impact on the network, and how do we make this Internet of Things happen in a sustainable way and in the most energy efficient way? And I think that's sort of the future where we're going. We don't have any specific ideas, but I think it's an interesting challenge to take on, and love to hear feedback from all of you on that. And if you're interested in the topic, let me know. I'd be happy to talk more. And I think I'll stop here, and thank you for your attention. Thank you very much.